yourself and share.
Thanks, Sam. So I'm David Hogg. I'm a computer scientist at the University of Leeds, and my research is mainly in the area of artificial intelligence, but I also lead a doctoral training centre on the application of AI to medical diagnosis and care, with a particular emphasis on cancer, which is how I come into contact with medical applications of AI. My talk is quite general, but I hope there's a pragmatic contribution to methodology in there, and leave you to judge at the end. So something uncontroversial, AI is advancing rapidly, it certainly is. Why is that the case? Well, number one, there's a huge growth in online data. In the medical area, we're seeing, as closely related to the first talk, Nelson's talk, access to a wealth of medical information from electronic patient records, genomic data, images, and even videos in some application areas. But more generally, there's a wealth of information online, not all of which is recorded because there's just so much of it. There's also an awful lot of innovation. So the computer science literature is absolutely stacked full at the moment with people working on new ways of doing stuff. So on the left there, you've got so-called ResNet, which is a convolutional neural network that's so transformed over the last 10 years image analysis, particularly in the medical domain, but in many other domains, image analysis work using these convolutional neural networks. And in the middle, the thing that's transforming text generation and text analysis, the so-called transformer. And then on the right, a different way of training the system, so-called adversarial approaches to training, which has been used in adversarial attack scenarios, where you actually show that you can generate images that will confuse or cause wrong predictions on the net on the left, the ResNet on the left. And this is kind of relevant to what I'm going to talk about later, where we see that these systems can do strange things, and sometimes very unexpectedly. And then finally, there's been a huge growth in computing power. So now Google's latest so-called tensor processing unit, TPU, if you have 4,096 of them, you've actually got an exaflop of power, which is a vast amount of computing power. So all of this has been put to good use, and there are many new applications emerging, medical diagnosis being one of the most prominent. Lots and lots of people worldwide working on the application of artificial intelligence in medical diagnosis and using all of that data which is becoming available, but also, again, relevant to medicine, development of new medical insight. You've got work by DeepMind on protein folding, work on autonomous vehicles, text generation, I'm going to say a bit more about that later, and playing games. Most of this work, actually, these applications coming out of some of the big IT companies. So one of the often talked about aspects of AI within medicine is the need for interpretability and transparency in the systems. And one of the observations that is made about deep learning approaches, of which the examples I've shown already are all based on deep learning, is that they lack transparency. And so what can be done in that direction? So I'm going to say a little bit about what is being done. This is a system from DeepMind, well publicized. It appeared in Nature Medicine in 2018. And this is to diagnose eye disease from OCT scans. And the insight that they had was that in order to give the clinician confidence in what the system's doing, produce an intermediate representation, a tissue segmentation map. So you start with the OCT scan, and rather than going directly to a diagnosis probability, go via an intermediate representation, which the clinician can look at and see that it actually does accord with their understanding of what's in the OCT scan. So these different colored structures in the middle here are actually different physiologically different structures within the macula of the eye. And then on the right, you just simply go from that tissue segmentation map through to a range of disease probabilities or referral suggestion confidences. Okay, so that's one way of beginning to deal with transparency, create some intermediate representations that make sense. Another is in the image analysis domain, and this is being used in medicine. My example here is not from medicine, with medical imaging. Draw attention in the image to those parts of the image that lead to the diagnosis. So if you're classifying a scan, a medical scan, as being containing cancerous tissue or not containing cancerous tissue, then show me the parts of the image that led to that part of the diagnosis. And this can actually be done quite successfully. Here's a simple example from the classification domain, where we're trying to classify things as cats and dogs alongside many other objects. And it's possible to, having classified an image as containing a cat, show me the part of the image that actually gave rise to that hypothesis. And likewise, if it's a dog, show me the part of the image that gave rise to the dog hypothesis. So we can do things like that using various attention mechanisms. And then third example is on causal models. So people have been working in the medical domain for a long time on producing causal models, probabilistic graphical models or Bayesian networks, where you represent probability distributions here on the nodes, and the conditional, the things that that probability distribution depends on are represented by these arrows. So it sort of represents the probabilistic dependencies in a system of random variables. And the idea being that maybe one could go from a deep net model and automatically produce a causal model. So that's a good, potentially a way in which one might think of actually trying to add some kind of explainability to what these deep networks are doing. But even with all of this, which does begin to give us some idea of what these networks are actually doing, there's still a problem. And that is that these systems, these AI systems, really have little in the way of common sense. And what I mean by common sense is the ability to think about things in a practical way and make sensible decisions. They don't typically assimilate non-verbal cues if they're looking at text. So the patient comes into the surgery and the doctor is aware of all kinds of things which are not within the medical record or are not conveyed verbally by the patient. They get so much more from the interaction. If you look at a patient record, an anomaly will just stand out to a clinician, wouldn't necessarily stand out to a computer system. And one of the problems is that these sorts of problems are completely unpredictable. You really don't know what's going to hit you. And the remarkable thing about people is we have this notion of common sense, and we know when something is not right. So you can think of the scenario in which AI is placed within a clinical environment. The AI task is this little blue thing in the middle here, but the real requirement, the thing that you're actually trying to do, is actually a much bigger circle and involves a much greater level of understanding of the human condition. Another way of thinking of it is the clinician in the loop provides the sense check. That's one aspect of what the clinician is doing. So you don't just leave the AI task to do what it does and then just trust the results and go away and act accordingly. It has to be situated within a wider environment where the clinician is actually involved. And this is an area of a lot of contention at the moment. What is the balance between what the AI is doing and what the clinician is doing when you start to introduce AI into the clinical workflow? So what I'm arguing here is think about the unexpected and think about the common sense that the clinician has that the AI system simply doesn't have. And the other thing that people have, of course, that AI systems don't have is empathy. There isn't an AI system that I'm aware of that has empathy in any real sense. Yes, there are systems that pretend to have empathy by nodding and winking and responding to you, but they don't really have a deep ability to understand and share the feelings of another. How could they? The book by Eric Topol, is arguing that this is so important that we really need to take humans to the next level, to up our humanist qualities. And these are the things that will always differentiate us from machines. So he wrote that in 2019. So I want to ask you, rather mischievously, I want to ask the question, just to show that it is hard, of how machine learning, how could we machine learn, how could we train a machine to exercise common sense and empathy? You know, what would the research project look like that tried to do that? Well, you know, why is it hard, first of all? Well, how do we learn? You know, if you look at the way that people learn, you know, we use our senses to sense things in our environment, and we've got a whole range of senses. So for a start, you certainly want to up the sensory capacity of machines. We learn to manipulate things by trial and error as children. So we actually explore the world ourselves rather than having it fed to us. We can learn factual knowledge and abstract concepts like sums, often with a teacher, but often learning things ourselves. We can make predictions from past experience. So we can go out in the street, look up at the sky and say, oh, it looks like it's going to rain. And we learn to be able to do these things. As I say, some of it is mediated by others in a teaching scenario, but most is actually gained by self-exploration in the world. So that's a major difference. We also learn within a really complex ecosystem. So the world in which we learn about things is a very complex world, starting from our early days, playing with parents and just playing with stuff, to the rich world in which we then move at a later age and as adults. I mean, just getting a little bit more offbeat, you know, actually our bodies have actually evolved in parallel with the ecosystem in which we live. So our bodies are not an accident. Our bodies have evolved along with our cognition, our ability to think about the world. So it's all part of the same kind of broader activity. And I think very important in the medical domain is that we also sense our inner workings. So the clinician has a hypothalamus that regulates the body's key processes and is aware of some of those things happening. So heart rate and blood pressure, body temperature, various balances, appetite, body weight, various secretions, etc., sleep cycles. And, you know, so a clinician in a very real sense knows what the patient is talking about when they talk about not being able to sleep, or feeling hot, or whatever it might be, because they have experienced themselves the same things. So it's not surprising that empathy is hard to. It's hard to imagine how empathy might be emergent within an artificial intelligence system. And therefore, you know, with empathy and common sense, it's therefore hard to imagine how the AI task, which is that little blue circle in the middle, could expand to encompass the real task when a clinician is meeting with a patient, which involves so much more. And certainly the ability to cope with unexpected things occurring. Today's AI systems actually learn in a very different ecosystem, you know, so they can learn from electronic patient records, yes, they can learn from internet media, they can learn from the Internet of Things, all those sensors around our homes, they can learn from playing, from video games. Typically they have absent or less capable bodies than us. Most AI systems have no body at all. Some do, but they're usually much less capable than our bodies. So they learn in a very restricted environment. So how would it be possible to go beyond where we are? Well, I just want to, you know, I don't want to finish by saying it all looks impossible, because I don't think it is. You know, what progress is being made that might point to the future in a small way? Well, one is there is this hypothesis of thought processes being mediated by language. So languages, the so-called language of thought hypothesis. It may not be a spoken language, but it might resemble it. So if we could capture language, maybe we could capture something about the cognitive processes that are going on in human brains. You know, the more that we actually live in a world which is that sort of the metaverse, to use that latest technique, which is actually the convergence of physical, augmented, and virtual reality. The more that we live in a world like that, the easier it is to capture all the information about the visual interactions we have. So maybe there is a future in which we could actually learn from the very rich tapestry of what people do day to day and all of the time. And I just want to finish on looking at some recent research, which is looking at this language hypothesis. It's essentially a deep learning model. It's based on a transformer, which learns to predict the next symbol in the sequence given the previous sequence. So this is what it's modeling. It's modeling this probability distribution. Given a sequence of tokens, words in a chunk of text, predict a probability distribution for the next word. Give me a probability distribution for the next word. I can then pick the highest probability word to continue the sentence, or something a bit less to vary the continuation. And this is what they did with a sequence of systems that have appeared over the last 3 or 4 years. GPT-3 is from OpenAI, and it's a system that learns this probability distribution from pretty much every scrap of text that's available on the internet, which is all of the written material produced by people over, well, a long period, certainly over the 20th and 21st century. This model has billions of parameters, and the number of parameters is going up the whole time as different people produce similar models, and you can generate absolutely remarkable pieces of text. So if you start the system off with this little bit of text in black, the system will produce character, or rather, token by token, but just think of it as character by character or word by word text like this. And it's really, in subjective experiments, it's really quite hard to tell that apart from what people have produced. So it's often people can't tell the difference between this text and what a reporter writing an article would produce. So maybe this is actually getting a little bit closer to capturing what it is thought is about. Maybe there is something in this, but I think it's still early days, because this is the whole written corpus of language that's obtainable on the internet. So there's an awful lot of stuff in there, and it turns out you can do things like this for free. You can say, make an outdoor pillow. Which of these 2 things should you do? Blow into a tin can and tie with a rubber band, or blow into a trash bag and tie with a rubber band? And you get, with this, based on GPT-3, you can actually get 81% accuracy on simple multiple choice questions like this that exhibit common sense reasoning. I've already mentioned sensory integration. So, perhaps eventually common sense might emerge from developments like these. But, without being human, how is empathy going to emerge? And I think I'll stop there. I was going to show you a little video, but I think given the time, I will just stop there.
Well, thank you very much, David. A really interesting talk about the future developments. So I think we can squeeze in one question if someone wants to ask anything.
Yeah. So a question from Alan Pang. When you say the false uncertainty, I always think of it the other way around, Alan. It's the false certainty that you get with an AI system. Do you mean that the AI system sometimes makes you question the clinical diagnosis that the clinician might make in a way that actually leads to self-doubt? What's the...
Oh, I'm sorry, David. We can't actually see the question, if you won't mind.
Oh, I'm sorry. It's the question is AI, as we try to incorporate AI systems within the clinical environment, how do we deal with the false uncertainty that AI systems can create when working with clinicians? Oh yeah, so yeah, wrong way around, right? Yeah, so the other way around, yes, I think it is difficult. I think in the longer term, it's a new way of working, isn't it? The clinician just has to learn to adapt. And over time, they will actually start to trust the system or distrust the system with different levels of trust. If the system is shown to be 99% accurate or 99.9% accurate on test data, and in your own experience, it seems to be making the right diagnosis, then, over time, one will build up confidence.
All right, thank you very much. And I just saw a question from Irene, which actually segues very nicely into Laura's talk, since that she'll be talking about exactly that. So yeah, Laura, please, if you'd like to introduce yourself and go ahead, that would be fantastic.